So a couple logistical things. First off, I neglected to mention this last week, but Annie's study group, I've added it just below my office hours. Annie's great. You should definitely go see her. Wednesday nights, she'll be in here. Anytime you just want to come hang out and work on the problem set, I guess do Friday, you can. Yeah, so yeah, it's just another resource. I just have lots of resources for you guys. The other thing is I'm using this software called Notion, and I'm still sort of getting used to it, but I really like it. But I'm trying to build this like database of all of our like classes, and then I've just started like I was working on this, and like it'll have all our meetings, our classes, our assignments. It'll have the links to the Zoom videos for each class and stuff, because I finally figured out how to get access to those. And then like, you know, like you can click on these and get assignments. One thing I really like about this is it has different views. And one of the views it has is a timeline view. So you can like see, you can like see things coming up. I don't know, it's a little strange to get used to it, but like you can like see a timeline of the course and what's coming up and what's already passed and everything. So I don't know, this is something I'm playing with, but hopefully you'll find it a useful resource. And then I'll try to, and I can just almost build this whole database for the class and then just link everything from here. So, but I'll try to post that. This is just my rough version of it. You can see what all my other stuff was on. I just realized you could see all my whole organizational scheme on the side there, but okay. And what else? A couple other minor logistical things, like I have a built-in grace period on assignments. I want you to turn them in on time if you can at all, but I do have this like there's like a 72-hour late window, whereas if you're just having a really bad week or something or whatever, I'll just be watching it to see like if somebody's turning in stuff late all the time. I'll start to like, I might have a conversation with you or just try to figure out what's going on. But if you're just like really busy one week and you need like an extra day on a problem set or something, then you can do that a few times. And so the Gradescope's still open. So if you look at Gradescope, it might even show you that it's like a problem set's still open after the official time it was due, but that's why. So that's one thing. And then the other thing, I think I've tried to say this, but we're gonna come down harder and harder on you, is like turn in PDFs. And you also do that thing when you submit an assignment where you like assign problems to pages. I think some of you, what I've heard from students is that once you submit your assignment, you can just click away from that and it's still submitted. So some students just skip that. But like you want us, like if you have problems, if the first 3 problems are on page 1 and you know the third problem goes on to page 2, then you have to you can click on problem 1 and assign it to page 1, click on problem 2, assign it to page 1, click on problem 3, assign it to page 1 and 2. That's when the graders grade, they don't have to go hunting for your problems. So if you don't, from the grader perspective, from my perspective, if you don't assign pages, when I click on one of your things to grade, it just says, student not assigning any pages. And then you have to start clicking through and finding the right page. And it gets annoying. So I will start coming down on you if you don't do that. Yeah. Then just assign everything to page 1. It's just easier. Anything that saves us clicks, right, is always like appreciated. It's like one reason I hate Blackboard is because to do anything I have to click like 17 times, and I can just almost do everything in this with keyboard commands and shortcuts and stuff, and a few clicks and stuff, and it all updates automatically to the web and everything. So yeah, so those are just logistical nonsense. Okay, I think, let's see, you've got a problem set and a video, problem set Tuesday night, video Tuesday night. I try not to kill you with the videos. I made one video about, I was gonna make 2 videos, one about lines in the plane and one about planes, one about lines in the 2D plane and one about planes in 3D space. And then I finished making the video about lines and it was like 23 minutes long. And I was like, okay, that's enough. I won't make them watch more than but it's a good thing to watch because then it'll lead nicely into the discussion we'll have together as a class on Wednesday. And it might be better to have that part as a discussion anyway. So So I'll try not to kill you with too many videos, but okay, I wanted today to, I mean, I know nobody's like finished the handout, but I think most of you got in pretty well into the cross product stuff. And so I actually want to talk about this projections stuff. And then I also, once we finish that, then I want to go back and talk about some properties of the cross product just to make sure we're all on the same page with how the cross product works. And I could have you do this in groups, but I think, I don't know, whenever I do this in group work, the students always, when I tell you to draw something, I get lots of interesting pictures that almost none of which are what I intended in my head. So maybe I should just, we could do it as a full class discussion instead. Oh, I probably should have been sharing screen that whole time. I'm still really bad at this. I actually found the videos and looked at a few of them and I thought I was like sharing screen and pausing the share. And then there's times that I'm like writing on the blackboard and talking and it's just the screen the whole time. And then there are times where I'm like talking about stuff on the screen and it's just me in front of the blackboard. I'm sorry, I'm trying to learn how to do this. So it's pretty bad, but I'm not sharing right now, right? So I can write on the blackboard. Okay, but if you're following along, watching, is anybody? No, okay. But if you watch this later, just go to the projections page on the vectors handout, which is page 3 or 4 or something. Page 4, okay, the projections section. All right, so I want to talk, just because there's this nice idea of projecting a vector onto a line, and it's going to come up a lot if you want to resolve, if you want to like break a vector down into 2 pieces, one of which is like parallel to a certain direction you care about, and the other is perpendicular to a direction you care about. There's like a nice, that happens a lot, like in physics applications and other places, and it's just a nice thing, and it'll come up in linear algebra if you take Math 2000 next semester. So let's talk about projections. Okay, so, right, so I said, let's have a unit vector U. So U, unit vector, I've never gotten good at the habit of writing the little hat. So I just try to state explicitly that it's a unit vector, and often use U. And so let me draw U horizontally. It doesn't have to be horizontal. I mean, this could be in space, you could be pointing off in some direction, but I can always like tilt my head and reorient space so that U's horizontal, right? At least from my perspective. So let's call that U. And that's a unit vector, and let's have V, some other vector. It's supposed to be straight. And I want to talk about the projection of V onto U. And so there's a line here, right? And if you do the, if you drop the orthogonal, then there's this vector, drop the perpendicular, drop the orthogonal, however, there's this vector right here. And this is the projection. So projection of V onto the line determined by U or onto U, however you want to say it, or maybe the line determined by U. But I've mentioned a few times before that it's useful to have a unit vector, to have just pure direction and not worry about magnitude, and you'll see why actually in this calculation. And this is written lots of different ways, but I think in our textbook it's written proj sub U of V, something like that. So that's a weird notation, but I think that's the way it's written. So different vectors, you could, it's almost like a function. It's like you're plugging in vectors and ending up with vectors on this line. Okay, and then the question is, but and it turns out there's a nice formula for this. And, oh, I guess there's another word called V parallel sometimes too. Or that's kind of the general projection. Or sometimes if we know the direction we care about, then we say parallel for the, this is going to be the part of V that's, it's like the part of V that's parallel to U, right? Okay, and so the real question is like, what is, how do we get the formula for this? And some of you saw some similar stuff when you got to the cross product and you were trying to show that the cross product formula with the area of the parallelogram was actually like the length of one times the length of the other times the sine of the angle between. There's some similar type things you can look at here. For example, what's the length of this? Oh, hello. What's the length of the hypotenuse of this triangle? V? Magnitude of V. V is not a number, but magnitude of V is a number. That's what's important to say there. So that length is the magnitude of V. And if this angle is theta, then what is this length? Magnitude of V times cosine of theta, right? Exactly. This is sort of a nice trig thing. So we could write something like the following. This is a little bit weird and maybe I should sort of say it. We could write, maybe I'll just say V parallel. Let me see if you believe this. So we could write something like this. Now this looks strange, I think, to students when the first time they see something like this. Yeah, that's good, right. The U is the direction, and then the magnitude of V cosine theta is like the magnitude of the vector. Right, this is a number. We can scale vectors by numbers. And certainly this should be a scalar multiple of U, i.e. V parallel is a scalar multiple of U. And then the question is, what scalar multiple, what scalar? And because using a unit vector, the scalar is exactly its length. That's why using a unit vector is helpful, because once you have something length 1, if I want something in the same direction of length 3, I just have to scale by 3. But if I have something of length like 7.5 and I want something in the same direction of length 3, then I have to figure out the right scaling factor. That's a little more annoying, right? So it's length. It's the one without the apostrophe, right? I think so, yeah. Please correct my grammar. I'm wrong. So it's length. So this is a number, and this is like I like the way Mano said that, which is like it's just like a number, which is its magnitude, and this represents its direction. Because whenever we write a vector down, we have to write out down both. Okay. Okay, but if you want to write that down, you need to be able to calculate the angle between. Except we've seen a formula for the angle, and in fact for the cosine of the angle. So a better formula let's use the dot product, right? Let's look at V dot U. By definition, that's the magnitude of V, by one definition, the magnitude of V times the magnitude of U times the cosine of the angle in between. Right? The right-hand side simplifies a little bit. Sarah's nodding. The magnitude of V parallel. Right, well, right, because why, what is happening here? That's 1, right? So this is actually 1. So this is actually just the magnitude of V cosine theta. So in fact, we can plug that in up there and rewrite V parallel, and this is what really looks weird, I think, to students, not to anybody, first time, few times we see it. We're all students of life. I can really write something like this. But this is a, trying to think of a better word for a mind fuck, but it's a it messes with your mind a little bit because this looks strange, right? But you have to just remember, this is always a number. So that's just a scalar. Any specific example you do, you'll get a number, and it's that multiple of u. And so this is the formula that you see in books. And also, it's nice that we use u because if it was not a unit vector, then you would, it turns out the formula is something much more horrible, like, well, not much more horrible, but it's something like if we use w not a unit vector instead of u, like if we just had some direction and we didn't scale it, then you see formulas for this in books too. I think it's something like v dot w over w dot w times w. So there's just, this is a special case when w is a unit vector, this just goes away. Because this is actually, and this is also the magnitude squared. Think of it that way. So it's just nice to scale things to be unit vectors when you're trying to project. I mean, you don't want to scale v because you're trying to project v, but if you're trying to project it under a certain direction, you do want to scale it. Okay, so that is the formula for the projection. Nice thing is it works in any number of dimensions. It also tells you something about what the dot product really measures. Some people think of the dot product as like, as this number is like the component of v along u. Of course, it only really makes sense if you use a unit vector, but you know, because it's like breaking down a vector into x, y, and z components. But instead of just x, y, and z, this is in some other direction. And so we're breaking down into that. So this is like, this is sometimes called the component of v along u. And this also makes sense that why we talked about the sign of the dot product being positive, negative, or zero. So if you got 0 here, they would be a perpendicular vector, and v would actually just crush down to nothing if v was perpendicular up to u up there. And if v was pointing at an obtuse angle, it would actually project down and be pointing in the opposite direction. So the component would be negative. Okay, fair. I think I said this number 22 on the handout. I think it's a nice thing just to check that it's always nice to do sanity checks in mathematics and say, like, does this make sense in some special cases that we have? So if we just say example, v equals, the most general vector I can write down is just something like this. Most general 3D vector I can write down. zk. And if we want to project it onto, say, I mean, what's the component in the I direction of v? It's clearly x, right? And you can check this. So v v parallel, or the projection onto I of v is by definition v dot I times I. But what's v dot I? If I dot this with just, if I dot x comma y comma z with 1 comma 0 comma 0, what do you get? You get a number, not a vector. X, right? You get x. You just get the x component, right? This is x, you know, basically we just dot this with I, we multiply like x times 1 plus y times 0 plus z times 0. So that's actually equal to xi. And so that makes sense, right? That's exactly what we'd expect to get. Okay. If you want to refer to the x component of a vector, you don't ever have to write x, y, or z again. You could just write v dot i, v dot j, and v dot k if you really wanted to. But that would be strange. So I gave this example. There's this problems 23, 24, 25. Or I guess, actually, let me talk about 24 first. Going back to this picture for a second. Or maybe I should just draw a new picture. If we have, just draw the picture again. If we have our V and our U and our line through U, that's why I made these different colors, isn't it? Then there's this V parallel like that. And there's also, so this is V parallel. And there's also this third side of the triangle, this vector here, which is also this vector here, if you'd like. Right, like, and it's clearly perpendicular, right? So this is sometimes called V perp. The green vector here. And the thing is, what equation can we write down pretty easily? Well, if we just follow, the vector from the whatever the origin, whatever this point is, out to V is the same as V parallel plus V perp, right? Just like almost in that example up there where it's like I could write it even in components as kind of all the different components added together, xi plus yj plus zk. And so that means that a quick way to calculate the perpendicular is just to subtract the parallel. Right? When you draw a triangle with two vectors, the third side's always the difference. And it depends on which way the arrow goes. And I always have trouble remembering if this is like, if I have just V and W, then what's this vector right here, for example? Well, I know if I add it to W, I get V. Therefore, it's V minus W. Or if I go this way, I add it to V, I get W. Therefore, it has to be W minus V. That's just the way I remember it. It's always hard for me to remember which direction is V minus W and which direction is W minus V. But that's another way to think about this too. It's like, what am I adding to V parallel to get V? Well, I'm adding this vector, so it's V minus V parallel. Good. Okay, so rather than get up for full group work, why don't we just do like 22 and 23 and 25 at your seats, but like introduce yourself to your turn and say hi to someone next to you and then work on the problem. Introduce yourselves if you don't know each other. Work on 23 and 25. We just talked about 24. I guess you can think about 26 if you finish 23 and 25 quickly. Just gonna write it on the board. 2i plus 11j. Bless you. You'll see I love 3/5 and 4/5 because that's like a nice Pythagorean triple. That's an 11, not a magnitude. Number 25 also, and check that your V perp is actually perpendicular to V parallel using the dot product. And again, if you finish those, you can think about 26, which is the general. Let's see if I remember what's going on here. Oh, did I make the numbers work out nicely? Sort of did, didn't I? Ah. Yeah, the final answer is nice, right? I mean, you can do, right, so you get 10u, but you can also write that out as, yeah, either ways. I mean, yeah, it's if you want an answer that's an actual vector, it's nice to sort of write it out. Okay, how are people doing with this? Is this? People found the perpendicular and checked that it's actually perpendicular? Yeah, you should take the dot product and see if you get 0. It's very satisfying. Hopefully. Did the perpendicular work, or have you guys tried that yet? Well, that's kind of how you're fighting the perpendicular, subtracting it from the parallel. But if you want to check two vectors are perpendicular, you dot product them and see if you get 0, right? You got 0. It's one of the times you're happy to get 0. Okay, so what did people find here? I guess I could write this as V parallel or the projection onto U of V. So what did you do? Someone tell me what you did. Yeah. Right, you just use the formula. And then when you found V dot U, I guess this is 2 times 3/5 plus 11 times 4/5. U. And this number worked out nicely to be what? 10. I think you get 50/5 total, right? So that's 10U. So you could stop there, or it's nice to write 10 times 3/5 I plus 4/5 J. Actually, I guess if you're going to do the V perp thing, it's nice to write this out in components. And that's what? You guys get 6I plus 8J. Great. So that's what the projection is. And that is a multiple of this, right? And then what's the perpendicular? What did people get for the perpendicular vector? What did somebody get? Yeah. So we do this minus this, 2 minus 6, 11 minus 8, negative 4I plus 3J. Good. And then if you dot the perp and the parallel together, if you dot these, because how do you check two vectors are perpendicular? You dot them together and see if you get 0. Does it actually work out? Yes. Minus 24 plus 24, 0. Okay, so that's how you can do that. Do the same thing in 3 dimensions if you like. I do like the argument of the general argument why there's a really nice, like number 26 on this handout says, use the dot product on the general formulas to prove that V perp is perpendicular to U, which means it's really perpendicular to V parallel, but use the V parallel throws in that V dot U, which is a little annoying. So it's easier just to show V parallel is V perpendicular is perpendicular to U. That was a mouthful. Show that V perpendicular is perpendicular to U. Not like U. Oh, not U. The letter U. Okay. Did anybody get that far and try it, writing it down? Yeah? And you got 0? It takes some thinking though, right?
Yeah. I actually wrote it.
Can I see what you wrote? Oh, nice. The interesting thing is though, is like, okay, so there's that. This is a strange, we'll talk about this. No, that's good. So let's check in general that V perp is perpendicular to U. I guess I should put like a question mark. V perp, the perp. So V perp dot U, it's sort of interesting to see what you get when you write this down. This is V minus V parallel dotted with U, right? But V parallel has a formula. This is where you have to be very careful with your use of parentheses, because this starts to look like a mess. Let's write this down carefully. It turns out the dot product has all sorts of nice algebraic properties, like it distributes over addition and subtraction. It's not that hard to convince yourself. So this actually is V dot U minus this thing, V dot UU dot U. This is where things start to look horrible. But I guess, because this is a number, which makes this a vector, and vector dot vector is number. So this is number minus number. So let's think about this last expression. What if I have like 7u dot u? Do you believe that equals 7? How? Well, if u is unit vector, how? No, it's hard to describe. I mean, you could think it's the length of this times the length of this times the area times the cosine of the angle between. The length of this is 7 times 1 times cosine of 0. But in general, and actually, but what if I turn this into like W or something? Right, I claim that this is the same thing as 7 times W dot W. Like if I do 7W dotted with W, that's actually the same as. So that you can actually move multipliers around like this, and it's kind of because of the reason we just said, like you could write this as like the length of 7W times the length of W times cosine of 0, which is 1, but that's 7 times, the length of 7W is 7 times length of W. Do you believe that? Times W. But there's actually this thing that this is the same as, this is the magnitude squared. That's actually an actual multiplication, not a dot product. And this is the magnitude squared, which actually is the dot product with itself. So yeah. So there's stuff going on here. So my point is you can actually, this is number times vector dot vector. I'm claiming this is actually v dot u minus, and you can actually do this. Basically moving the number outside the dot product. This looks like mumbo jumbo, but it all does, you can convince yourself all of these are valid steps. And then u dot u is the magnitude of u squared, which is 1 squared, which is 1, right? And so this is a 1 right here. And so we just get v dot u minus v dot u. Which is 0. So amazingly, that really does work. Yeah, I mean, there is a multiplication like there, I guess. But all the dots, I try to make the dots bigger. Like over here, these were these small little dots were multiplication of numbers. And this was a big, yeah, I should be careful, right? There's a little tiny dot there, which is multiplication of 2 numbers. And then I don't know, scalar multiplication, number times vector. You just don't write anything. Okay. So that's amazing. That does work. You just have to really be able to move the algebra around in nice ways. If you call, maybe, I mean, if it still looks really weird to you, it's like call this C. Then I'm saying that cu dot u is C times u dot u. It's just C is a complicated looking expression itself. It's helpful. Okay. I don't know, I'm just always amazed that that works, how that computation works out. Feels very like math proofy. Okay, so that works in general. All right, what else do I want to say? Are any questions, sorry, just before I move on, any questions about projections? Parallel v perp. Yeah.
Is there like an analog to this in 3D where you can like project something down to 2 dimensions?
Yes. it's more of a linear algebra thing. It turns out what you need, yeah, like how would you project onto a plane? It turns out you don't just need 2 unit vectors, you actually need 2 unit vectors which are perpendicular to each other so that they don't interfere with each other kind of when you're projecting. Then you can just like project onto each one and then add them together. But that's actually a big topic of linear algebra, like how to project, like I want to project from some 7-dimensional space onto some 5-dimensional subspace. There's like formulas to do it and stuff. And the 3 to 2 is the natural. But like down on the 1 dimension is pretty easy. And then to do 2 higher dimensions, you just have to be very careful about. It actually is just a sum of projections on the 1 dimension. You just have to make sure the dimensions you're projecting onto are perpendicular to each other. It's like, I mean, this is actually a fascinating question. And it's like, you know, if you want to just project a vector onto X and Y, to get the components, it's clear those are perpendicular. That's important that we chose the axes to be perpendicular to each other. But if you choose 2 non-perpendicular directions and then choose a third vector to project onto it, well, you would end up with this vector and this vector as your projections. And the thing here is if you project this vector onto these 2, then this vector is actually the sum of its projections. But here it's not. If you add these 2 orange vectors together, you don't get back the red vector. And so, but again, this is more like Math 2000 stuff, but it's kind of cool. Like that's important. That's a reason why we choose our axes to be perpendicular. It's nice. and one of those reasons is that a vector is the sum of its projections, which would not be true if the axes were not perpendicular to each other. So good. Yes. I don't know what we would do if we lived in a parallelogram world where we just really liked, well, you could do everything on a hexagonal grid if you're like 60 degrees. You could tile space with equilateral triangles. So maybe that would be nice in some ways, but we seem to like square grids the most. Okay, anything else? Why is there a pair of binoculars up here? Administrator, oh, someone's watching us. That's what it says. Okay, well, so let me share screen for a minute. Sorry. Just to, so we covered all of this, and then I won't do this in class, but it's kind of nice, like why the 2 definitions of the dot product are the same. But it does use this thing. I mean, you're kind of pushing the mysterious part into just an identity from trigonometry, which is there's this generalization of the Pythagorean theorem that actually is called the law of cosines. Like if A and like if you have a right triangle, A and B are perpendicular to each other, then the cosine of the angle between is cosine 90, which is 0. That last term goes away, you get back to the Pythagorean theorem. There's a generalization called the law of cosines, and then if you just apply the law of cosines to this triangle and write everything out really carefully, you can actually end up with exactly that formula. But then I always feel weird about that because I'm not proving the law of cosines for you. I don't even know if I could do that off the top of my head. There was a point in time when I could have done that off the top of my head, but I don't think that point is still, I don't think it's still true. I have to think about how to prove the law of cosines. So, but it's sort of nice. It's like, it's interesting. Okay, and then just for the last 7 minutes, I just want to make sure we're on the same page with some of the properties of the cross product. Right, so here's the definition again, or well, algebraic definition, the geometric definition, which again, it's a vector, so you have to specify the magnitude and the direction, and it's perpendicular by this right-hand rule. And the magnitude is the area formed. I will say that I had you guys do some examples just to get used to it. And there are some things, actually, if you look at these properties like D and E, we actually use similar properties for the cross product, for the dot product just now. right? We use the fact that the dot product distributed over addition and subtraction. We use the fact that you can move constants around like this, like right here or here. And I use the distribution over there. So like they are considered products because they do satisfy certain things you would want multiplication to satisfy. Like they behave certain ways that you would like a multiplication to behave, like they distribute over addition. And so these are kind of, for the cross product, these are kind of hard. Well, maybe not this one as much. This one is just kind of like comparing some areas of some parallelograms where you double the length of one side. It's not too bad, or scale the length of one side. Seeing this is a little bit uglier, but you can draw some pictures and convince yourself that the areas of the parallelograms are the same and that they point, well, I guess if V and W are not in the same plane as U, it gets sort of hard actually to picture this to be true. You could certainly derive it from the algebraic. So the algebraic definition. You could, like the geometric definition, it's sort of hard to prove something like this. Maybe from the algebraic, you could just write out the algebraic definition and it would be really ugly, but it would work. You know, meaning up here, if you had a third vector and like wrote out all these formulas, and it would work, but it would be kind of unpleasant to show. But I just want to see some of the important things, like the anti-commutativity of it. So like, yeah, let me go back to the cross product. So let's just write down some properties of the cross product that are important, and that you can sort of justify from either the algebraic definition or the geometric definition. And then if I have a moment at the end, I'll say something about why those two definitions are actually work out to be the same, which is not obvious at all. But yeah. So properties of the cross product. Oh, let's see, this is what I do. I forget to stop the share. Okay. So one property is this anti-commutativity, this like, if you do V cross W, you get minus, sorry, if you do W cross V, you get minus V cross W. And you can certainly see it in the formula, the algebraic formula, if you just switch the V's and W's in the algebraic definition, you're able to pick up minus signs if you just swap all the V's and W's. But also in the geometric definition, like, because it's a right-hand rule, it's really, you know, if I have V and W, and I guess I'm thinking of V is closer to me and W is farther away, then V cross W would be in this direction, because I'm going from V to W. Say this is closer. This is farther, farther. I think farther if it's actual physical distance. Yeah. Go over it. Yeah. The way I always think of it is point my fingers at the first vector V, curl them towards the second vector W, and then my thumb is pointing in the direction of the cross of the right-hand rule direction. And here it's perpendicular to both, right? That's a perpendicular. Wait, how do I write a perpendicular? Like that? Anyways, but if you do W cross V, you point your fingers at W, curl towards V, which is closer. You have to turn your hand upside down to do that. And so this is direction of W cross V. But they both have the magnitude, the same magnitude, because they're both the area of the parallelogram, right? It also follows from this or either definition that if I cross product a vector with itself, I get 0. because if I put, for example, if I put V in here for W, I get V cross V is negative V cross V. Oh, I did something wrong though. That has to have an arrow word. Yeah, and also, right, if you have, what kind of parallelogram does the same vector make with itself? A flat parallelogram, right? So it has no area. Also, I was talking to one group last week about this, and it's like, what would be the perpendicular direction if you had a vector in itself? There's lots of potential perpendicular directions. So it's better that this is 0. That's a couple things. Oh, and the last thing I'll write down is just that, I think I said this on the next page. It's kind of fun to check this like geometrically, but I cross J is K. Are we late? 9. J cross K is I. And K cross I is J. So I think I wrote something like this last time, that it's like, if you put I, J, and K in a circle, although really probably I should be here and K should be here because I'm thinking of the axes. Then you do I cross, you kind of go this way. I cross J is K, J cross K is I, K cross I is J. And if you go the other way, you get the negatives, right? By what we just said above. And you can also check this with the algebraic formula. And that was that weirdness, that weird asymmetry I talked about, how like the y-axis is sort of different from the x and z axes, or the xz plane is different. So there's just some weirdness there. That's good to keep in mind. Okay, I think I'm out of time. Oh, and I didn't talk about the magnitude, but maybe I'll say a couple of things on Wednesday. But we'll talk about lines and planes on Wednesday. All right, thank you, everyone. Have a good rest of your day. Oops.